Hello everyone. In today's video, we're going to begin an analysis of the ideal Atwood machine and solve for the accelerations and tensions in a way that is not typically done in a high school AP physics class, nor in a college level course on general physics, where students are typically introduced to this topic. The reason for this somewhat rare approach is that after watching nearly 3 dozen videos on the topic and reviewing nearly a dozen college-level textbooks, invariably, I found their approaches wanting in two areas. First, there was not enough explanation on the implications of the ideal assumptions, that is, on what makes the Atwood pulley system ideal. In this series of videos, we'll see this is critical to solving the problem and to understanding the underlying physics of this rather sophisticated problem. And second, there was not enough explanation on how to establish and interpret the sign conventions used. These videos are intended to address these gaps and hopefully reveal a deeper understanding of the complex dynamics of even a simple pulley system. If successful, this approach will demonstrate that many of the traditional assumptions are neither obvious nor trivial. Now, in order to get the most of these videos, I suggest two prerequisites. The first is a familiarization of forces as vector quantities and their relation to acceleration. That is, the viewer should have some experience using Newton's second law. And second, the viewer should be familiar with the mathematical definition of torque and its relation to the vector cross product. And finally, because the slide deck is dense, I recommend the viewer pause the video at each slide transition and read or skim the slide before continuing on with me. Now, here's the agenda of how we're going to proceed. You may wish to pause the video and briefly skim how the videos in this series are organized. Okay, so let's get into the problem. I've taken this problem verbatim from one of my favorite texts, Physics for Scientists and Engineers by Raymond Surway. I've had this text for more than 25 years and continue to find it insightful. The problem is taken from chapter 5 in the 3rd edition. It is example 5.4, called Atwood's machine. And the problem reads, when two unequal masses are hung vertically over a light, frictionless pulley, as in the figure below, the arrangement is called Atwood's machine. The device is sometimes used to determine the acceleration of gravity. Interesting comment, but not very useful for the solving of the problem. And finally, they give us what our requirements are going to be. Determine the acceleration of the two masses and the tension of the string. Okay, so immediately we see that we are given information that the pulley is light and frictionless. Great. But what do these concepts mean, and how do they relate to the problem? These are examples of hidden assumptions, and they appear in even one of the sources I have found to be one of the best. Now, to be fair to Surway, he does this most probably because the full analysis requires concepts that are not provided until much later in the textbook. Here, we're going to bring these concepts forward in order to understand how the problem gets solved in introductory classes. Now, let's look at the figure on the left and see if we can get additional information. Well, from the pulley diagram, figure 5.2a, we see that the bleed marks are perhaps indicating that the masses are moving. And I suppose we should be able to infer from the yellow bleed mark under mass 1 that it indicates that the mass is moving up. And the red bleed mark over mass 2 indicates that it is moving in a downward direction. I don't think these publishing conventions are obvious to first-time learners, but after many years with textbooks, one sees the pattern. From this general sense of motion, I suppose we're being asked to conclude that mass 2 is greater than mass 1. Now on the right, we see the free body diagrams. And here we find from the general direction of the acceleration arrow that our initial guess about the relation between the masses, namely m2, is greater than m1, is probably correct. Furthermore, we're told that the acceleration is the same for both masses, and so the tension is the same on both masses. As we shall see in this video, these assumptions are not at all obvious. Essentially, Survey has circumvented or hand-waved a great portion of the analysis by providing or giving these details in the free body diagrams. Because no explanation is provided at this stage, one would have to assume that the value of this problem is to get the student to practice solving systems of equations. While this skill is important, this approach eliminates much of the physics behind the Atwood machine. And lastly, I'll make mention of the fact that no sign convention is provided in the free body diagram. Although this allows the student to select her own, I think it is poor practice to not provide a sign convention in the free body diagram. As we shall soon see, it is as important as providing units in your solutions. So we just saw that Survey is solving the problem where M2 is greater than M1. In video number 4, we'll reproduce Survey's solution. Now, however, I propose we solve the opposite problem, that is, where M1 is greater than M2. I'm doing this because I found examples of this problem to be more rare, and because it will help us see the importance of sign conventions later on. That is, we'll have 2 example solutions to compare. Now, let's review the free body diagram. For M1, we have 2 forces acting on it. There is a tension force from the string pulling up on M1, and we have labeled that force T1. We show the direction of T1 to be in the up direction. There is also a force due to gravity, which is the weight of M1. The magnitude of this force is M1 times g, where g is the acceleration of gravity near the Earth's surface. There are also 2 forces acting on M2. A tension force T2, which is due to the string pulling up on M2, and its weight, which again is shown as M2 times g and points in the downward direction. There are also net accelerations for each mass, which are the result of the interplay between the forces acting on each mass. For M1, we have a net acceleration which we call A1. And we assume that A1 is pointing down because we are told that M1 is greater than M2. And similarly for M2, we have a net acceleration which we have defined as A2. A2 is assumed to be pointing up because we are told that M1 is greater than M2. Now, note that all accelerations and tensions are generalized. We haven't made any assumptions at this stage, or simplifications. Furthermore, I've chosen the sign convention that up vectors are positive and down vectors are negative. And I show this on the right-hand side of the slide. And I use this convention because it is consistent with how first-time learners learn the XY coordinate system. It is the simplest and most direct approach. That is, nothing special is assumed. Now, let's review the equations. We have, using Newton's second law, positive T1 plus negative M1 times g for the weight of M1, which we rewrite as minus M1 times g, and that equals to the net acceleration times the mass of M1. And the net acceleration is given as negative because we have assumed that A1 is in the negative direction. And we can bring that negative sign out and rewrite it as negative M1 times g. Similarly, we have positive T2 plus negative M2 minus g, which we've rewritten as minus M2 times g, equals positive M2 times g. A2 is shown as positive because we've assumed that it is up, and we've assumed that it is up because M1 is greater than M2. Now, notice in this most generalized case, we now have 4 unknowns and 2 equations. The unknowns are T1, A1, T2, and A2. So we need more information in order to solve this system. And here's where the hidden assumptions come into play. The first hidden assumption is that our string is inextensible. This just means that our string doesn't stretch, like a rubber band. Now, in practice, all strings, cords, and ropes stretch or give a little bit when placed under tension. In our ideal case, we assume no stretching occurs. What we will now show is that the result or implication of an inextensible or non-stretching string is that the magnitude of the acceleration of A1 and A2 are the same. That is, the magnitude of A1 equals the magnitude of A2, and therefore both can be replaced by a single constant, which we'll call A. Let's motivate this with a simple thought experiment. In this experiment, both masses start at position 0, and both masses are initially at rest. Now, we're going to pull M1 down a distance x. Since both masses are attached via a non-stretching string, they will both move a distance x. The directions of the displacement, and therefore the signs, are different. M1 moves down and M2 moves up, but the magnitudes are the same. That is, x1 equals x2 equals x. Now, since the displacement occurs in the same time for both masses, we can conclude that the velocities and accelerations are the same. We can see this derived in the equations in step 3. And since velocity is the change in position over the change in time, and since the change in position is x, which is the same for both masses, and the change in time, which is t, is the same, we can conclude the velocity of each is x over t. Again, the same for both masses. And since the acceleration is defined as the change in velocity over time, and the fact that the velocities are the same for both masses, then the changes in the velocities over the changes in time are the same. And therefore, we can conclude that the acceleration is the same for both masses. Now, we can take our result that the magnitude of A1 equals the magnitude of A2 and replace both with a new acceleration, which we'll call A. When we update our equations, we now have 2 equations and 3 unknowns. We're making some progress. Our next goal is to find some relationship between our tension forces T1 and T2 so we can solve this system of 2 equations. This will require that we take a deeper look at how a pulley moves. And to understand how a pulley moves, we'll need to introduce 2 new tension forces, T3 and T4, which are shown in the figure on the left. T3 and T4 are tension forces due to the string that act on the pulley and not the masses. T3 generates a torque that causes the pulley to rotate in a counterclockwise fashion. And similarly, the tension force 4, or T4, acts on the pulley, causing it to rotate in a clockwise manner. These new tension forces acting on the pulley cause it to rotate, and they are competing in different directions. T1 and T2 are the same as before, and so are the weights. These forces act on the masses, M1 and M2. Now, our goal is to show some relationship between all of these tension forces. We'll do this in 2 steps. First, by using assumptions 3, that is, the pulley is massless and frictionless, we'll show that T3 equals T4. And second, by using the assumption 3, the string is massless, we'll show that the magnitude of T1 equals the magnitude of T3, and the magnitude of T2 equals the magnitude of T4.